Excuse me. All right. So welcome everybody to the Robert Ferguson Observatory Speaker Series. I'm Stephanie DeRomelar, and we're thrilled and honored to have Dr. John Bonnell with us today, and I'm going to introduce him in a moment. But before we start, just wanted to remind everybody to please keep yourselves muted to minimize background noise. And then we will open up for questions at the end. You can feel free to put questions in the chat as Dr. Bonnell is talking, and I'll facilitate those at the end. And I think he's also okay with people, unmuting yourselves and asking directly if you'd like as well. So just to give a quick little intro on the Robert Ferguson Observatory, for those of you new to our organization, we are run by the Valley of the Moon Observatory Association, which is a 501(c)(3) nonprofit comprised of volunteer, amateur, and professional astronomers. And RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for almost 25 years now. The observatory is almost all volunteer run, and in a typical year serves about 9,000 people annually. We're located in the beautiful Sugarloaf State Park, and the observatory houses a 40-inch reflector telescope, the largest telescope in Northern California that's accessible to the public, a robotic 20-inch research grade or CCD telescopes, and an 8-inch 2-meter long refractor telescope. We've kept the presentations in our speaker series free to the public to align with our mission of offering educational-based astronomy programs to our community. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, you can do so through our website, which is rfo.org. So now to introduce Dr. John Bonnell. He did his undergraduate work in physics at UC Berkeley and worked in the Space Physics Research Group at the UC Berkeley Space Sciences Lab while a student and during a pair of gap years before graduate studies. He did his doctoral studies in plasma physics and electrical engineering at Cornell in the Space Plasma Physics Group, working on spectral and interferometric studies of auroral waves and their role in ion acceleration. After Cornell, Bonnell took a postdoc with the Space and Atmospheric Physics Group at Los Alamos National Laboratory, working on mesoscale auroral electrodynamics in the auroral oval and polar cap and characterization of ion distributions across the day-side magnetopods. He took his current position as a research associate and project physicist at the UC Berkeley Space Science Lab in late 1999. His focus since the early 2000s has been the design, implementation, and use of electric field instrumentation for heliophysics applications. He's been involved in several NASA satellite missions as a hardware and science team member. And since 2013, he's been actively involved in the NASA Sounding Rocket Program as a principal investigator, co-investigator, and member of the Sounding Rocket Working Group, and has brought geospace sounding rockets back to the Space Sciences Lab after a nearly 15-year hiatus. So without further ado, I will go ahead and hand it over to Dr. Bonnell. Thank you so much for being here.
Oh, you're welcome. Thank you for having me. And thanks to RFO for setting this stuff up, and to you and Chris for recruiting me to this. I'm excited to share. I'm excited to share some results that we got that led up to and were taken during the NASA Greece sounding rocket campaign back in 2014. Before I get started, I'll take a minute to thank the score of people who were involved in this, engineers, scientists, managers, technicians, both at UC Berkeley and at the Southwest Research Institute, Goddard Space Flight Center, and all the folks at the Wallops flight facility where the sounding rocket program is led. Also, old and new colleagues back at Cornell, Steve Powell, Chris Chaston, and Don Hampton and the whole University of Alaska Fairbanks Geophysical Institute Poker Flat Research Range team that provides the logistical support up in Alaska for the NASA Scientific Sounding Rocket Program. Let's see, where's the button that makes it go? There's, okay. So what I'm gonna what I'm going to give you all is first a primer on the aurora, what it is, what we know about the processes that cause it, some interesting behaviors of the aurora that still puzzle us, and what we're doing about investigating those processes, trying to explain them with physics, electrodynamics, using rockets, cameras, and science. Now, it's you know, if I were there in front of y'all, I'd ask for a show of hands for people who had actually seen the aurora. You know, I think it has become a far more pervasively known. There you go. There's somebody very good. All right. With the advent of inexpensive, good quality low light cameras, it's become a far more pervasively viewable phenomena, for lack of a better word. And so a lot more people have seen it through YouTube or through television programs. But in terms of actually going out and seeing it, it's interesting. You know, it's unclear to me who's been up far enough north to see it lay itself out like this. Now, but that for those of you who have seen it or haven't seen it, but are not familiar with exactly what's going on in it, the classical way of talking about the aurora is that it's an electrical phenomena. It's not a spark. It's very much like an old school television screen or a cathode ray tube. And what happens in a cathode ray tube is you use electrical energy to accelerate electrons towards a screen with phosphor on it. And you raster it around, and that produces the emission of light that produces the images that we see on an old school cathode ray tube TV screen. The similar sort of thing happens in the aurora. What you have is that there are natural processes that occur at altitudes several thousand kilometers above the surface of the Earth that accelerate charged particles like protons, or in the case of the visible aurora, electrons, down along the Earth's magnetic field. And these energetic particles strike atoms and molecules such as oxygen, nitrogen, nitrous oxide, that can be found up in the very tenuous parts of the Earth's upper atmosphere, altitudes of 100 to 300 kilometers, 60 to 200 miles. And by striking them, energize them, when those particles or when those molecules de-energize, they often give off light, and that leads to the aurora that we see on the ground or from above on other planets. And so a nice still photo of the aurora here from the ground. This is from someplace up in Canada. Beautiful sort of curtains of greenish light spread across the sky. This is a time-lapse image of it. And I know that because I can tell there's all kinds of interesting stuff going on that's getting blurred out because of its motion. But Earth isn't the only place where one can observe aurora. With the Hubble Space Telescope and other imaging assets, people have found that there are aurora around the poles of Jupiter. So this, I'm not sure if you guys can see when I'm pointing with my cursor. Is that something that you guys can see? But anyway, this panel up here in the middle right is a picture in ultraviolet of the auroral emissions around one of the poles of Jupiter. And there's beautiful sorts of things. Similar sort of thing here in this lower right, where you can see superimposed on a regular optical image of the excuse me, of Saturn, the auroral emissions that happen around its pole and different sorts of things. All right, so.
And Dr. Bonnell, we can see the cursor move, just so.
Oh, excellent. I'm glad of that. You know, folks who know me know that I do a lot of like poking and pressing and showing stuff. So, okay, so. All right, so what is it though? How is it that you get this? With a television screen, you plug the thing in. There's some electronics. It makes this accelerating electric field. There you go, accelerate electrons. How does that happen? What is it that provides that source of energy for this process in the natural world. Well, so it turns out that the Earth is not alone out in space. Space is full of all sorts of interesting tenuous ionized gases, magnetic fields, electric fields, and it's the interaction between between two particular things: the fast ionized wind that blows off of the sun and out into the solar system, and that wind blowing across the lines of the Earth's magnetic field essentially it's a form of a generator. And that generator, like all generators, extracts electrical energy out of mechanical energy. It slows down the solar wind as it flows past the Earth, and in slowing it down, it drives electrical currents down along the magnetic field lines that then close through the conductive ionized parts of the Earth's upper atmosphere, so-called ionosphere. And that closure of currents down there and the flow of currents both drive the flow of the ionosphere and also lead to interesting smaller scale things that happen along the magnetic field lines that then become what we call the parallel potential drop, the electric fields that exist along the magnetic field that accelerate these electrons and produce the auroral emissions like the ones that you can see here. I think this is actually, it's nice. This is usually you see pictures of the northern hemisphere and you see the northern auroral oval. But this actually is a picture, I believe, of the south. There's Australia up here, the Antarctica, and you can see kind of like how monks have that little tonsure, the little ring of hair. It's like that. It's not that the aurora is right up here at the pole where the solar wind can come straight in. It's actually out here on the edges in these regions that correspond to the boundaries. And it's basically because of this flow across the boundaries and other things that happen at those boundaries that you can get these acceleration processes happening and you get the aurora that you see. All right, well now, so to get more down into it, as those accelerated charged particles, they get accelerated through potential drops of anywhere between 100 volts to 100,000 volts. So that sounds like a lot compared to what you're used to dealing with in your domestic service, but the kinds of potentials that you get associated with, say, lightning in thunderstorm are often millions of volts to billions of volts. And so, the magnetosphere, it's nothing to sneeze at, but thunderstorms are bigger. So, but when those electrons come down along the field lines, the kinds of things that they strike and the kinds of things that produce most of the light we see in the aurora are things like oxygen, nitrogen, and nitrous oxide. And those different species of gas have different concentrations as a function of altitude. And also the kinds of light that they give off are changes as a function of altitude. That has to do with whether they're colliding with each other and basically giving up their energy as collisions rather than as photons coming off. But what that does is it produces this beautiful, just absolutely festive gradient of color in altitude. And so this panel over here on the right-hand side is it's a view of an aurora that's not way off on the horizon. It's fairly close in, but it's not directly overhead. And so it allows you to see the curtain-like or sheet-like structure of it here. But it also allows you to see that up here at high altitudes, there's this beautiful red, which oftentimes turns into rays called the tall red rays. And then as you work your way down, you get to this sort of beautiful green color. And then as you get even further down, when the brightness is quite high, there's another red line that comes in down here, turns things to be more of a white color. But the key thing is that you get this beautiful gradient, and I'll be able to show you that in some all-sky camera images that we use as part of our way of figuring out when we can launch. But anyway, so this is the kind of thing, most of the time down here in the lower 48, what we end up seeing is maybe this red up on the northern horizon, or we might see the green poke up above it. But in general, we don't get to see a full-blown display overhead. And that's probably a good thing, because that would mean we were having a Carrington event, and that would be not okay. So anyway, but the key thing that I want you to get out of this is that the light that we see in the aurora is really just the tip of an iceberg that goes all the way out, to several thousand kilometers altitude along the magnetic field, and then all the way out to 100,000 kilometers out where the Earth's magnetic field connects into the solar wind. And the sorts of structures at tens to hundreds of kilometers across that you can see sort of spread across the sky that just sort of develop over the course of the night. Those large scale things are driven by larger scale electric fields and current systems that are associated with the plasma flows that are happening out there in the magnetosphere, and with pressure gradients that occur because of density and temperature differences. But none of that large scale stuff can explain the fine scale stuff that I'm going to be showing you. Where do those small scale and rapidly varying structures come from? So there's a lot of theory and observation about that attempts to explain that sort of behavior. This complicated set of plots up here in the corner, in the upper right corner, have to do with showing it's a numerical simulation that was done that started with a relatively smooth and simple distribution of electric field in altitude and horizontal distance, and then with an arc that was just and that this would turn into an arc of light emission that was relatively simple and smooth. After a very short period of time, the vertical structure of that electric field has been broken up and enhanced. The arc is broken up into waves and blobs, and the flows associated have become all kinds of vortices and curls and things. And so this large scale thing, it's an equilibrium, but it's not a stable one. And so and that's the thing that you can see when you actually look at, let's see, yes, okay. So what I'm going to show you here, this is a movie made from what's known as all sky camera footage. What this is, I'm going to just get this started so that we get away from this big purple thing, which is the sun still being up. Okay, so what this is, it's essentially a fisheye lens. And so the zenith is here in the middle. The horizon is all the way around the edges. The northern horizon is here. The southern horizon is here. I can never remember if it's what you would see when you lay down or if it's the mirror reflection, but that doesn't really matter. For purposes of talking about this, it's really what I'm going to show you is over the course of an evening, how these auroral displays that are associated with a phenomenon called substorms. These are large reconfigurations of the magnetic field and the flows out in the magnetosphere on the night side of the Earth, and how those things get manifest in what you can see on the ground. So here it's about 5:30 local time, and the sun is setting over here in the southwest. And if we run the camera forward a little bit, you can see the moon is here traversing across the southern horizon. And let me see, where do I need to stop? Okay. Let's see here. Almost there. I think we're almost there. So what I want you guys to do, or y'all to do, is to focus on what's going on down here at the northern horizon. And the colors and the quality of this, it's scientific imaging, so sometimes it's not the most fancy because it has to sit out in the cold for long periods of time, and so it has to be more robust than a fancy camera. But what you can see starting to happen, oops, sorry about that. do this again. Okay, so what you can see happening down here at the bottom of the picture in the northern horizon is that you can see those tall red rays, and you can see that green lower border here. And my colleague from Cornell, Steve Powell, he's the best for terminology. He calls them the little red arc of the north and the little green arc of the north, because when you start seeing the little red arc of the north, you're like, okay, maybe we might have some action this evening. When you see the little green arc of the north, you know, oh, this might actually turn out to be a night where we can launch and we don't have to eat, you know, microwave food anymore. It'll be great. So what you'll see happen here up at the northern horizon is you'll see this green border brighten, and then you'll start to see a little bit more structure in it. And that's one of these substorms happening. And so, oh man, I wish it would stop doing that. Okay. Okay, here we go. All right, that's a little bit further on. Apologies on my clicksmanship here. But anyway, what you see is that the red boundary above continues. This green lower border brightens up, and you start to see various sorts of structure and motion in it, or apparent motion in it. And that's the hallmark of a substorm. And what I'll show you next is what that looks like when you're right underneath it. So if we do that, you get into a recovery phase where you can see all sorts of sort of speckly green aurora that's happening equatorward of this main auroral feature. And then it calms down again. And basically we're waiting for the magnetosphere to build up. It's a little bit like a geyser, maybe, you know, build up some stuff. Oh, my goodness. Okay. All right, here we go. All right, so here we can see the green and the red is coming overhead, and all sorts of stuff is happening. And here in the course of just 2 minutes, we go from this faint stuff to bam. The sky is full of swirls and curls. This corona effect that you could see there is the arc standing straight overhead, and the ripples and things moving by. That is the hallmark of one of these substorms. And there's some of that structure, the largest scale horizontal structures of it, that can be explained by what's happening out in the magnetosphere. But a lot of the fine scale stuff, like stuff that's coming along here, and these ripples that come along at boom, 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 that is, you know, that has to happen down at lower altitudes. And that's one of the things that we're trying to understand. All right, so now, since it's been trying to get to this one for so much, all right, this is a white light image that's taken over a much smaller box of the sky. It's about 10 degrees on a side, looking right up into the zenith. And this is at, you know, the all sky camera stuff was at time lapse. It was about 10x or 60x. I can't remember exactly. This is 1:1. And what I want you to look at in this one is, you know, there's a lot of stuff that will happen, but what I want you to see is how we go from this sort of bland, unstructured, relatively dim display to something that is full, just absolutely full of interesting little whirls and curls and things that just say that you know, if you're used to watching water flow by in a river and eddies develop and flow, you'll just be like, look at that. That's fluid dynamics happening right there in front of me. So let me go ahead and run this for you. So you can see there's starting to be some stuff, things moving along. And again, you're starting to see things. We've developed 3 sort of bands here. And look at this beautiful, beautiful stuff that's going on up here. Just whirling, you know, and what, you know, when we look at this from the ground, you know, we're seeing that it's like you've got a row of these cathode ray tubes, or these accelerators. And instead of it staying as like a nice smooth sheet, that sheet is getting twisted up and turned around by some sort of fluid dynamic process or an electrodynamic process. So, the question then is, so I'm just gonna, this is the only math that I included. If we look at how fast those curls get moved along and, sort of the apparent motions that are present, we can, and we know how the ionized gas should flow. That tells us, just from geometry, we can guess that those things are moving at about 20 kilometers per second. So that's almost 740 miles per hour against each other. It's well above the sound speed in that gas. It's and it corresponds to a really intense electric field at those altitudes. Compared to thunderstorm electric fields, it's very small, but compared to the kinds of things that you usually see, it's an order of magnitude bigger than what we usually, than what we see at the ground, what we see at lower altitudes. And so for Greece, the question that we proposed to study was, if you fly an instrumented payload over the aurora and we fly through those energetic particles that cause the aurora, and we measure the associated electric and magnetic fields, and we observe the light from the ground, in different wavelengths with very fast resolution, we can come to a better understanding why there are these small and fast structures in the auroral light. So how do we get to do that? How do we get the resources, the logistical and the technical and the financial resources to actually build this payload and take it in the field and launch it to 300 kilometers altitude up in Alaska in February, for goodness sake? So the great thing, NASA, most of us, growing up, we're familiar with the big NASA projects, things like Voyager, things like Galileo, things like the Perseverance rover that you'll hear about later in this series, where NASA says, here's a project that we're going to do, and we're going to put a big pile of money, James Webb Space Telescope. We're going to put a pile of money and keep adding money to the pile for decades until we finally get this amazing telescope. But NASA has several other kinds of things. One of them is this low cost access to space. And what this is it's an annual competition for rocket, balloon, high altitude balloon, and CubeSat access to space. And typically there are 1 to 3 new starts per year, and they get 3 to 4 years of funding, totaling somewhere around 1 to 2 million. And that's about 4 or 5 person years worth of work. And what NASA is doing is they're providing the ride and saying, tell us the science you want to do. Tell us where you need to go and tell us the science. We'll get it peer reviewed. And if it passes peer review, we'll get you there. And so we proposed this back in 2011. We were selected in 2012. And the particular kind of launch vehicle that we were given was something known as a NASA Black Brant 9. It's a 2-stage solid fueled sounding rocket that's about 45 feet tall, fully assembled. This is a lovely picture of a Black Brant 9. Not sure where this is. This is not up in Alaska. I'll show you a picture of one in Alaska. But just to give you a sense of how tall a person is, that's the red bar down here. The first stage is this part that's white. The second is this part that's black. And then the scientific payload is up here in the top. And depending on what kind of scientific payload it is, you may keep the nose cone on, you may throw the nose cone off. So, but that's what you get for that. So what does this look like in the field when you go up to Alaska? Okay, so this is a really great picture. So the launch facility up in Alaska is in this big valley that's about an hour northeast of Fairbanks, Alaska. So there's no place to stay on base. There used to be. It was terrible. They finally demolished it and got rid of it. So you stay in Fairbanks and you drive over the hill and worry about moose and blizzards and bad weather and bad roads. But anyway, this is a really nice group shot that we got probably on our dress rehearsal day with most of the team that was involved from both all the university folks and all the NASA folks, and then the rocket in its styrofoam box here. Well, I'll talk about that in a second. In the background, the lead scientist on this was Dr. Marilia Samara, who at the time was at the Southwest Research Institute. She's now at Goddard Space Flight Center. Here she is. She's standing with Steve Powell, who was an engineer I worked with back in my graduate school days, who was just one of the real bright spots in the field for several decades. And there's a lot of, like most sort of field campaigns, there's a lot of, it's not folklore, it's superstition, because you are waiting for nature to do something for you. And so one of those things that was picked up by the campaigns, because we do launches up in Norway, there's a snack bar or a snack cracker, a snack cookie that's sold in Norway that's called Quick Lunch. But when you look at it, it looks like Quick Launch. And so it's traditional to give the PI, at least in our part of the field, to give the PI one of these as sort of a token, like, okay, here we go, we're going to do this. Again, to give you a sense of scale and what this thing looks like. This is Marilia and our Standing Rocket Project Office lead, John, standing next to the actual launch pad. The rocket is hanging from a rail. This is like a big arm that you point in the direction that you want to go and then launch. The rocket is encased in a styrofoam box, and warm air is flowed up through that box, because in Alaska, you can get down, when we're in these launch conditions, it's typically 30 below, maybe 40 below. And if you don't keep the rocket warm enough, that cold can seep in, it can crack the solid fuel, and instead of a launch, you get an explosion. And why do I know this? Because I saw it happen. It's no fun at all. Nobody gets any data. And so you build a styrofoam box. That's what you do with it. Protects it. Like all field projects, it's kind of arduous. You're working long hours during the day when you're building it up, and then you switch to a nighttime schedule, because our prime time for launch is between 10 o'clock at night and 2 o'clock in the morning. So you become night owls and set yourself up to do a launch. So this was our planned launch. We would launch from the base down here to the north, out into the wilderness of Alaska. We would achieve our apogee over our downrange optical site at a small settlement called Venati, and with the idea that we would wait for conditions such that there would be an auroral arc sitting overhead at Venati, and we would fly over at the same time, get viewing from above, viewing from below, probing from above. All right. So, so this all gets codified into some launch conditions. We counted for 24 nights over 5 weeks. It was a long time. We were a little bit silly by the end of it. I'll show you some beautiful stuff. We had beautiful aurora overhead in some cases, but aurora overhead is not aurora that you can launch into. So, luckily this particular team, we were not very formal, and so the log is full of things like, shh, the magnetosphere is sleeping. but we counted for 18 nights, and then we got into a situation where the moon was up and spoiling, and would have provided enough light to spoil the optical stuff. So we went home for 2 weeks and then came back, counted for another 7 nights. And finally, on the night of the 2nd of March, 2014, we launched. Now, just to give you a sense of what night 5 looked like, what exciting and tantalizing looks like, that's what exciting and tantalizing looks like. That's overhead at the Science Operations Center, which is about a mile up the hill from the launch site. It was absolutely gorgeous. One of the students and engineers that was working for me, she at the time was reading the Golden Compass, and she's like, "This is just like the Golden Compass." Oh my God! So, but all, just beautiful, bright aurora, shimmering curtains flowing overhead, all of these sort of mobile rays and things. And then this just sort of gives you a sense of what sort of scientific infrastructure they have up there. It's a big building, really much nicer than when I started as a graduate student 30 years ago. There are domes where there are semi-permanent cameras or spectrometers or imagers or other sorts of things with heaters to keep them so that they can do observations and all that sort of stuff. But that's what night 5 looked like. But this is what the launch night looked like. So we launched at 11:09. So I can't remember exactly what time that was. It was pretty late at night, before midnight, but definitely not. But anyway, so we launched, and so this frame on the left, this is a single frame from high-speed video, and what it shows is the first stage firing, as well as these small, what are known as spin motors, that basically you have fins to spin the rocket up, but the rocket isn't moving fast enough when it's coming off the rail to really get a good spin on it. And so what you do is you have some small rockets that help spin it up, and that gives you a whole lot more accuracy in your trajectory. And then this picture here, the NASA has started providing these sort of glamour shots of all of the launches. But what it really does, this is a 60-second exposure that gives you the launch, the first stage out to burnout, and then these 12 seconds where you're waiting for the second stage to go, and you're hoping that it is, and then you finally hear it kick off, and then the second stage firing. And then this here is the arc that we flew over, that was hanging right overhead at Venati, right where we wanted it. So, but the sense that this lights up the whole valley when it goes off, that's totally the way it is. Oh my goodness, those solid rockets are so bright. So what we actually, so the trajectory that we actually flew, we flew for 600 seconds. So about 10 minutes flight. So 5 minutes up to apogee, another 5 minutes all the way past. We made it up to about 335 kilometers altitude, right overhead at Venati. Hooray for practice, hooray for hard work. And so what did we fly over? All right, so this is, I'm going to intrude this picture, and then I'm going to show you the view. This is going to be a 10x normal speed. The south is at the top, the north is at the bottom. So this is just like the other all sky camera. This is a all sky image. It's just the green line emission. So the lower altitude structure. And then this little point here that you'll see traverse its way across is the mapped location of our payload down along the magnetic field to where the aurora is happening. And what you'll see happen as we fly along, so you can see these are bright auroral arcs. You can see that counter streaming, the curls, all that kind of stuff. And as we work our way, as our foot point works our way across, we're just inundated in all of these eddies and flows, all this bright auroral emission. And basically it was the arc that we were looking for, that we were waiting for. This beautiful, this right here, just that stuff sweeping right across us. That is, that's what we wanted to be immersed in order to be able to compare what we could see that of the stuff that was coming down to make the aurora and what the aurora was doing from below. All right, so a little bit more technical views of what we observed. So one of the key things that we looked at was the flux, the number per square centimeter per second of electrons at different energies that were coming in along the magnetic field line from above that then produced the aurora. And we had an instrument that measured from about 200 volts up to 30,000 volts. And which is the range of energies that you need to see in order to see most of the energetic electrons that come down. And so the intensity is plotted as a color, with the blue being low intensity, the red and reddish brown being the highest intensities. And that's plotted as a function of energy and time. And the key thing to get from this is that here, these features here where you see energetic electrons that start at, say, 2000 volts, go up to 6, go up to 20, and then drop back off and fall away. This corresponds to when we were flying through the brightest parts of the arc. And so that's what you expect to see. It means that we saw something that makes a lot of sense. These sort of ghostly things that are hanging out here, we're still looking into those. We're not really certain what that is. There's certain electromagnetic phenomena that are associated with it that are fascinating, which I can go on and on about, but I'm not going to go on and on about right now. But anyway, point is that our electron detector did the thing it was supposed to do. It gave us very high time resolution, 30 of these spectra per second, basically lined up at the same sort of cadence that our ground optical stuff was doing and that our electric and magnetic field measurements were being made. So we have a really high time resolution view of what's happening in the electrons that will eventually produce the auroral light, and the fields and flows that are associated with them. This is another sort of very busy plot, and I apologize for that. But this is two components of the electric field. The main thing to know about the electric, to see in the electric field is that on these edges of the aurora and associated with these funny little spicules out here and with other things in here, there's all sorts of enhancements in the fluctuation levels of the electric field. And that means that there's electromagnetic waves that are coming down, and we're seeing them happen. But it's not the 20 or it's not the 100 millivolt per meter fields that, if those fields up at the highest altitudes were just mapping all the way down, they're much smaller. They're a few millivolts per meter to tens of millivolts per meter. And that was one of the science questions we wanted to ask is, in association with these small scale rapid flow features, do you see the signature of that in the electric fields at low altitudes? And the answer is no, and there's good reasons why you shouldn't, but it was a thing that we went out and tested. And that's the key thing about this, is we went out and tested it. Let's see, what else do I have? These are, again, this may be a little bit too much insider baseball for people. But one of the ways that we look at the electric field data is, so we'll look at it as a signal in time. But what we'll also do is we'll break it out in time and frequency. And this allowed us to see that when there were times when the swirls went by, we would see the frequency spectrum of the electric and the magnetic fields in a particular band from about 1/10 of a hertz up to 10 hertz. You would see that increase in amplitude. And so, we're still in the process, even several years later, because more rockets come and you get inundated and you don't get your stuff done on the first one. But it's quite clear that when the swirls go by and the curls go by, we're seeing these bursts of fluctuating electric and magnetic fields. And in essence, it's sort of like it's almost like the echoes of the process that's happening up at high altitudes. We're seeing kind of the echoes and the shattery noises of it. Like we didn't actually get to see the glass break and these small scale structures form, but we're seeing all of this sort of electromagnetic debris that propagates down along the magnetic field as waves, and gives us hints about what's the process that's producing all of the small scale structure. That's a lot of words about that. Again, what we're actively doing is that there are ways to go into the auroral images, excuse me, into the auroral images and actually quantify the swirliness, the vorticity that's present, and compare that to what we see in the fluctuating electric and magnetic fields through the filter of different models. Again, this is some work that Chasten has been doing, and that is ongoing stuff. But anyway, so I have a lot of other technical things that I can share, but that's the meat of the fun part of the talk. Well, the sort of big level 0 fun of the talk. There's plenty of other things that I can show you about the payload, about the ground imagers, more detailed stuff about the data analysis. But I just want to say thank you, Daniel. That's all for now. And thank you for your interest and time. And I'm happy to answer any and all questions that you guys have at this point.
Thank you so much. That was really, excuse me, really interesting. And so please, if people you can either unmute yourselves or write things in the chat. We do have one question, which is, what does an electron telescope / detector look like? Can you describe it?
Sure. So what I brought up here, this is actually it's a schematic diagram of the whole payload. And unfortunately, it doesn't give you the best view of what that instrument actually looks like. The electron detector is this brown one up here called APES. We like to give them cute names. But what you have with an electron detector is, in this case, there's an imaging plane, which is a bunch of essentially it's a bunch of solid state diodes. And when an energetic electron comes and hits one of those diodes, it produces a pulse of charge, and then you register that as an electron hit. And in order to break out the electrons by energy, there's a strong magnetic field. The electrons come in, and the lower energy electrons have a very tight radius of curvature. The higher energy electrons have a much larger radius of curvature. And so along the face of the detector, you go from low energy to high energy, and you sit there and you read that all out, and each time you read out the slice of the detector, that's telling you the number of counts in that chunk of time. So that's one of the ways that you can do it. Almost always there's some sort of deflection by a magnetic field or a magnetic field that depends on the energy or the momentum of the incoming particle, and then some sort of amplifying, a phosphor or an electron amplifier system that gives you the answer. Does that satisfy your curiosity about electron detectors? Let me see if I can make the chat a little bit bigger.
And the same person also asked, how do you correlate the electric field and the visual?
Yeah, so there's the classic correlation by eye, like, ooh, look, there's a curl, and ooh, look, there's some fluctuation in the electric field and the magnetic field. So that's what we do when we're sitting there on the ground getting excited when we first get the data in our hands. But then what you do to do something more quantitative is, based on the theory of how electromagnetic fluctuations develop and propagate in the auroral environment, you can make predictions about how bright the aurora is, how fast it moves, what sort of scale sizes it has, and what sort of electromagnetic, the amplitude and the phase of the electromagnetic waves that you should see coming out of it. And then you can compare that and see, is your model correct? Do you understand the parameters? So it's mediated by a model, like most things. But there's also just sort of the raw, like zero order, wow, look at those cool things happening together. So does that address your question? Who was that? That was George Lawyer.
Yes.
Okay. Okay. So
one person raised their hand. I don't
Bruce
know.
Peterson. Yes.
Yeah. Bruce, feel free to unmute yourself if you'd like to ask a question.
I think I did. Can you hear me?
Yes. I can hear you, Bruce.
Okay. Good. Thanks, John. I really appreciated that. That was interesting. I understood maybe 10% of it, but that's pretty good. Feeling good about that.
I'm glad. Thank you.
But I wanted to ask you kind of a personal question. The one time I saw the Aurora, we were at Denali at early September. So it wasn't, really, really cold and really dark, but it was fine. But what we saw was like a really hazy cloud. We didn't get much substance in it at all, but we were tourists. So we took lots of pictures and the pictures were fabulous. Okay. And I was wondering, like, is that pretty typical that, using a camera, we'd see it a lot clearer than we did with our eyes? That's
what I've found. So the last field campaign that I was on, it was in Norway, and it was the first time that I'd been in the field with people having just like their cell phone cameras. I was shocked at how good of pictures they got. I mean, you could, there was this beautiful like shawarma and pool bar that was run by some Syrian immigrants. And so you could stand out on the porch and look to the north, and you could see the Aurora on the days when we weren't working, of course. And they would get beautiful things. But yeah, your eye, sometimes your eye captures things that you don't necessarily see very well. But yeah, sometimes you can see a lot of structure. I mean, if I go out and in the afterglow of the substorm, when there's a lot of these pulsating patches, it's really pretty hard to see the contrast with your eyes. But with a good camera or video or imager, you can see the contrasts, and particularly if you're doing some filtering and things. So
excellent. Thank you.
You're welcome. I'm glad you got to see it. Denali, we went on a field trip to Denali. It was closed, but it was okay. That was fun. Oh.
It's an amazing place.
Oh God. All right. Is there anybody else who had their hand up? Otherwise, we can move on to the next question in the chat.
Yeah. The next question is, do you distinguish sky glow as a different phenomena from the classic auroral displays?
So in the sense of the physical process that's producing the light, in general, you don't. It's the same transitions, molecular or whatever, or atomic, that are producing the photons that you're seeing, but the thing that's energizing stuff is different. So sky glow, typically sky glow is all about recombination after ionization from solar, ultraviolet, and X-ray fluxes. Sometimes there's collisional things that are going on. Sometimes there's heating processes that are going on. And so, that it's, it's so cool about all of the pictures that you get from ISS. You can always look at them. You can see the little green edge, the sky glow. And I'm like, look at that. That's, people are so used to seeing like sunrise and sunset, but they're like, there's the upper atmosphere doing something cool. And so, so yes and no. The light, the process that's making the light is the same, but the thing that's energizing the molecules and the atoms to produce the light is different. And it's a much lower intensity phenomena. Like typically, the aurora, the brightness of aurora measured in a unit called a Rayleigh. Like a kilorayleigh is sort of visual. Sky glow is typically less than a kilorayleigh. And so you have to integrate for a long time or have a very sensitive camera to see it. And then auroral, those sorts of aurora that we were seeing, those were tens of kiloraylie's, and the really popping ones are like 100 kiloraylie's. So, but anyway, does that address your question? All right, excellent, cool. That's a good one. I like that one. All right.
And then John McCoy, lots of Johns today. John McCoy asked or said, thanks, John, for the new perspective on auroras. Do you have more flights coming? What detectors do you dream of having?
Oh, that's a good, those are good questions. So since Greece, so we launched Greece in 2014 from Alaska. I was a co-investigator on a campaign where we did 2 rockets together out of Norway back in 2018. My graduate student and I are going to be going up to Alaska for another. It's interesting. It's sort of an Aurora adjacent launch in March and April. We're using, the Aurora again because of the electrodynamics. It drives different sorts of flows in the ionized and the neutral gases. And this is it's a flight by a colleague of mine at Clemson, where we'll do a launch and we will look at the flow of the neutral gas and the flow of the ionized gas in order to see where the two uncouple. Normally they're coupled by interparticle collisions at low altitudes, and then slowly they decouple and the neutrals start to move on their own and the ions move on their own. So we're going to fly through that transition region and look at it. But it's also one of these really cool ones where, in order to get the best view of what the neutral winds are doing, they're going to do chemical releases. And so like the Azure flight that some of you that you may have seen, it's if you just YouTube Azure Auroral rocket mission, you'll see some beautiful chemical releases that were done up in Norway several years ago, where they use luminescent stuff up at high and then chemiluminescent stuff to sort of track the winds and provide the background. So we've got that coming, and then we've got another Norway campaign later this year in the October-November timeframe, as long as, again, it's contingent on COVID and stuff like that. But in terms of detectors that I dream of having, so these, what I'm actually, there's a couple of different electric field dream electric field projects that I'm working on. One is it could fly on rockets, but it's much more meant for orbiting satellites. It's a project that we call Grotifer. And some of you, any of you who are familiar with like little microscopic life forms, the rotifer is an animal that has these 2 crowns of cilia. And we came up with a thing. One of the things that's hard to do is measure all 3 components of the electric field at the same time with the same accuracy. And so we came up with this wild idea of 2 sets of antennas that rotate relative to each other like gears. And you measure really well in this plane and you measure really well in this plane, and together you get all of it all the time. And that's going to be, it's hard enough to convince people that you're not going to wrap your antennas around the spacecraft, let alone if you've got them interdigited as gears. But that one is it's very exciting. It's been an idea that's been kicking around in the community since the 70s, and just was the path not taken. And about 10 years ago, people started getting excited about it. We started doing development work in terms of the controls and the engineering and the whole process. And I'm working with my mentor, Dr. Forrest Moser, who's now 92 years old and still very active, and one of our new researchers, to sort of keep moving this along and hopefully get it built in the next 10 years. So that's one thing, to be able to measure all of the components well at a high rate is really important. So that's kind of a dream detector. I mean, there's plenty of other things that are a little bit more technical. So anyway, so that's the story there. There's plenty of other things having to do with the optics and the electron or the particle detections. You want to go faster. You want to be able to see with better resolution and angle, because that allows you to constrain your models, to constrain your, the tests that you do on your hypothesis just that much better. And that's super, super satisfying. So how about that? Mr. McCoy.
I actually had a question, probably a very simple question. So forgive my ignorance. I'm the director of RFO, but I am not an astronomer myself. So, but I was just wondering why you just see the aurora around the poles. You did a really good job of explaining the interaction between ionized gas and the magnetic field. So why is it not visible, closer to the equators?
Right. So what it comes down to, let me go back to one of my diagrams.
And I love the picture with seeing it on Saturn too. It makes sense, but I didn't really.
Isn't it amazing? It doesn't have to be true, but it is. So the key thing, so this, that's the thing. People are like, oh, the aurora happened and they happen above, the North Pole. No, they happen around it, and it's because really what's happening is, the phenomena that produce the currents and the electrical power have to do with the boundaries of the magnetosphere. And those boundaries, so at the highest latitudes, the magnetic field is just open out into the solar wind. And you can have energetic particles coming down. So for example, if there's a big solar flare, the reason why transpolar flights will redirect is because there's a higher flux of essentially MEV particles coming in and producing secondary showers because of that direct access. But those fluxes and the amount of energy per unit time per unit per square centimeter that comes in because of that direct particle access is minimal. You do get patches up in the polar regions, but the real meat and potatoes of the interaction happens down in this collar that corresponds to all the field lines that either map out to this boundary in the front or map out to the boundary in the back, because that's where the shears are happening. That's where currents are flowing out there that can get diverted down into the thing. So it's all about, basically it's telling you there's a boundary out here. And then when you get down to lower latitudes, you're away from that boundary. The flows are much smoother, they're much more stable. And so you can get aurora. There's an aurora known as the Great Red Aurora that happens at low latitudes, but it's driven by a very different sort of process. It's driven by things that have to do with the radiation belts dumping particles into the atmosphere because of different sorts of storms. It's not driven by this sort of, it's not really friction. It's all about generators, and the generators all happen on the boundaries, and the boundaries map to this little tonsure of hair at the North Pole and the South Pole. So it's a little bit hard it's hard for me to explain without delving deeply into a whole bunch of math. But the idea is that it's due to things that happen on the boundaries of the magnetosphere, and those map to very particular places in latitude.
No, that's interesting. And actually and I would love to see them in person. That's a kind of a bucket list thing. I have not seen the aurora in person myself. One person asked, what made the aurora your passion?
Oh, so it's interesting. It's not like I grew up thinking about the aurora, but astronomy is like the one of the gateway drugs to physics, right? And also like geophysics. Like I grew up as a kid in the early 70s, and there was, I grew up on things like nova, and there was a whole series of stuff about the sort of popularizing the idea of plate tectonics. And so the idea of geophysics was always interesting to me. And when I got to college and had an opportunity to work at the lab, I didn't know anything about space physics. But to me, what was really cool about it is that it is like this giant open air electrical engineering extravaganza. It's like, I'd always worked with electronics, and so I was interested in how electromagnetic stuff worked. But this was like fluid dynamics and electromagnetic theory, and then also it was this amazing natural phenomena. The first time I saw the aurora, back in 1993 on my campaign, it comes at you from the north like a thunderstorm. It's intense. Just that, like this whole thing coming at you, like, what's going to happen? And so, it's a real synergy, I guess is the right word, between the kinds of things that I like to think about in a quantitative sense, but also just, really, a real attraction to cool things that happen out in nature. And here's one where and it's space too. So look at all that. It's a pretty easy trifecta. Oh, I don't know.
Awesome.
Okay.
And I'm sorry, I know we're a little over time. Do you have time for a couple more questions?
I do. I'm glad to hang as long as it doesn't ruin you all's schedule.
Well, we had a couple more. One was, as we enter a more active solar cycle, are we more likely to see aurora in our area?
So short answer is yes. And I think that there's actually, in the last month or two, there was a couple of good size solar flares and what are known as coronal mass ejections associated with those flares. A coronal mass ejection is just this big loaf of solar plasma and magnetic field that's thrown off as part of the process that produces the X-ray flare. It propagates through the solar wind and then impacts into the Earth's magnetosphere and produces auroral substorms and things. And I know that we were getting, because of that, we were getting auroral, nice auroral displays down into Minnesota. It's hard to, like I said, it can be, if we were getting auroral displays this far south routinely, that might be catastrophic, because it takes a very large perturbation to essentially, because the auroral oval has to do with where the boundary is, to get aurora down to where we are, you got to peel this onion down pretty far, which means that the solar wind is blowing pretty hard, means that the magnetic fields are very strong. Excuse me, which means that there's going to be a lot more electrical power being driven in to drive these things, these electric currents, as they fluctuate in time. They fluctuate slowly, but they're big, and that dB/dt induces currents in the long transmission lines, and can either overload them and shut them down, turn them off. This happened up in Quebec back in the 80s. It's happened in a couple other times since then. And so it's could be cool, but also could be dangerous. So but anyway, yeah. So, but I think that the opportunity, so that you don't have to go to Norway, that you don't have to go to Alaska, you just have to go visit your in-laws in Minnesota and go to the boundary waters, or go up to Seattle, or, well, Seattle's kind of rainy, probably a bad idea, but someplace nice and dry, like the middle of Saskatchewan. That's a nice place to go. So anyway, so yeah, it's definitely the case. And the opportunities as we ramp our way up to the next solar maximum are going to be, keep an eye open. There's a place that NOAA maintains. It's called the Space Weather Enthusiasts Dashboard, and they provide a lot of insider baseball stuff with like satellite observations and solar wind stuff, but they also give you a nice little map that shows the auroral oval and their prediction of how far south and how intense the aurora are going to be. And so that's definitely a thing. It's a very lightweight thing. It's kind of fun to watch. We used it. I learned to use it when we were out on this campaign, and I still go back and check it out, even though I'm not going to see the aurora. So that's, there you go. That's that. And somebody asked about the payload, which is that's a good question. So for our kinds of payloads, we in general do not we we don't like put a parachute on it and recover it. It just crashes into the tundra. Since the early 2000s, the environmental impact agreement that the Geophysical Institute has with the indigenous population and with the state of Alaska says that they have to make a good faith effort to recover the stages and the hardware. And that has been enabled by the fact that we carry GPS navigation systems on our payloads routinely now. So you have at least a better chance of knowing where it's going to, where it was before when you last got contact with it. And in fact, I have pieces of this payload in my office that were recovered. And boy, you can tell it hit hard. I will tell you that, the industrial plastics that we use for certain parts of this thing, they turn into the most delicious looking marshmallows you've ever seen. And a huge deck plate that we hogged out of aluminum that has gears and things. If I had thought more about it, I would have included some pictures of it, but you can see which side that poor thing hit, because it's just like stove in. And and then the other pieces that stuck out, those are all torn off and everything. But anyway, it was amazing. And so we in general will recover those. And there is concern, the upper state, the stages of the rocket, rocket fuel is high explosive, and it's not toxic the way that hydrazine is, but it's also not the natural thing to have out there. It's typically aluminum in some sort of polymer binder. So you don't want that leaching out. And so you try and recover it as best you can. All right. Anything else?
There was one more question. Have there been any detectors flown to detect electric field directly in auroras of other planets?
So, yes. I think that the best example of that is a mission. Oh, let me try to think. You know what? I take that back. There hasn't really been one. There have been. So I think that there was planned to be some electric fields on the Juno mission that is in orbit around Jupiter now. And it would have been a perfect platform for doing those electric field measurements in the auroral region on Jupiter because of its high inclination flying through those regions. But I believe that the electric field instrument was de-scoped because they couldn't figure out, how to have enough mass and everything for it. You can infer, by doing your energetic electron measurements, you can infer the presence of the electric fields. But yeah, it's definitely a thing that has not happened on other venues. It's definitely something that the planetary community is thinking about, particularly the folks that are interested in the aurora-like phenomena that happen over the crustal magnetic anomalies on Mars. So I've talked, sort of spitballed how many kilos, how much money, how much data would be required to fly a simple electric field instrument to sort of measure the electromagnetic phenomena associated with those aurora. It hasn't been manifested, and we will see when it happens. But nevertheless, yeah, that's a good question. And that, again, it will be fascinating to see what, whenever you go out there and you actually measure it, it looks like terrestrial aurora. Is it? Let's see what it is. So there you go. Anything else?
I believe that was all the questions. And again, I apologize that we went over time a little bit, but thank you so much for all your thorough answers and for putting this together for us. It was really wonderful. And
well, thank you all again for the invitation. Thank you for the lovely and engaged audience. That's my favorite. It's I very much enjoy sharing sharing this stuff with folks. It's important to let people know, all the different things that are happening out around us, to get them to go out and do things and get them excited about exploring it. So again, appreciate the opportunity. Thank you all for your time.
Thank
You guys stay safe.
Thank you.
Have a good one. Hope the rest of the series is pleasing to y'all. I'm going to stop sharing.
Thank you. Thank you so much again, and have a good rest of your evening.
Great. Thank you.
Bye,
Thanks so
everybody.
Bye,
much.
everybody.